kind of collective operations are available in the MPI standard, and I will give some examples here, and you can be able to follow some exercises with these examples. First thing I want to discuss is the synchronization. And the first point I would show that it takes some time to do the synchronization. So I have written a small program to find out the timing of synchronization. And I will show you this. This is in a directory /MPI -call, and there's a program which is called sync. I show you what this program does. Here I have the files in my folder MPI -call. There's one program called sync.f. And you see this does nothing but calling barrier in between two calls to the time routine, and the difference will tell me how long one barrier takes to execute. Then I will record this time for every process which participates in the barrier. And I look for the largest time with the reduce and the operation maximum, MPI max. I will find the largest time all processes for this barrier execution. See whether I have loaded the modules. So I have to load modules. The MPI implementation. I have to file, effort, program, and then I run this program. So I start with one process, then no synchronization is necessary, but then I an idea how long the overhead of timing will be. Oh, that's spade. Oh, yeah, it's written. It came without synchronization, just with one process. I have 0.1 microseconds. Now I look for processes where really synchronization is done. Area is done. So I see it's about 1 microsecond. 0.1 10 to the -5 is 1 microsecond. Now, if I have to synchronize more processes, say 4, see the time is increased to synchronize more processes. I do the same. You see the time is very much scattering because I'm synchronizing processes in a multi-user node. So I don't know what the cores are doing for other users. So it's not very clear that you have every time the same timing for this. But let me proceed with more. Then the time is rising, and even 16 processes, even larger. So you see, synchronization takes time, and it takes more time for synchronizing more processes. Now, to get a feeling synchronizing is about, I would suggest to you to write your own barrier, your own barrier to synchronize processes. How is this done? Just think about sending a small one word message from every process to process 0. And if process 0 has received a message from every other process, it will signal to all other processes that this stage has been reached. And after this, all processes are sure that they are at the same point in the program and they can proceed. I suggest to you to write this simple program in this handmade, self-made barrier. And you can start just with a skeleton file where everything has been written with, except just the exchange of the message from all processes to process 0, and then the signaling from process 0 to all other processes, which you should do yourself. You can start with the program sync _s, which means self-made. And if you don't succeed, or if it's too long, you can look up the solution in this directory, MPI course _solution for the different languages. So I will give you 5 minutes, or say, 5 minutes to complete this task. At 9:15, I will continue. If you look into the directory MPI course, solutions, say, for the language F. See, there are a lot of files, and one file is just sync s_r.f. You see what has to be done. All tasks except task 0 send a message. You make a loop over all processes, tasks from task ID 1 in proc -1, and if this the task is IP, then you are sending. Otherwise, you are receiving. You are at task 0. You are receiving from this task IP. Short message, count one element. And then after this loop, you do another loop where task 0 sends a message to all other tasks. So again, a loop over all other tasks, 1 to nproc minus 1. And if your task ID is 0, then you send the message to task IP, and otherwise, if in this loop your task ID MID is equal to IP, then you receive this from process 0, from the source 0. So this is just the 2 loops you have to do. Okay. I think we can finish this one. And you see, this is a way to do synchronization just linearly in the number of processes. Well, that's a good question. Let's think about it. It might be correct that it's enough if the receive is blocking. Okay. I think, Jakob, you are right. It would be enough to send from task 0 to every other process. Okay. Might be enough. But I would like to show that it's possible to optimize this kind of communication, synchronization. We did it in a way to send a message from path 0 to every other process, one after the other. So this would be take a time of proportional to the number of processes, but you could do it in a way, in a parallel way, that at the same time you make a communication between processes, half of the number of processes apart, the total process apart. So process 0 communicates with process 3 in this case, and process 1 with 4, and so on. And then these pairs of processes are already synchronized, and then you can synchronize these pairs again in the next step, and then you process the last 2 groups of processes. So that would be a cascade-like synchronization, which is faster and takes only the time proportional to the logarithm of the number of processes. That's the way these kind of collective processes are implemented in the implementations. I have a example implementation for which is valid with the number as a multiple of 2. Okay. Now we want to discuss the broadcast, a very simple example. For distributing input values from process 0 to other processes. So that's often a task you have to do. You have an algorithm with some input values. You will read these input values with one process, and then from a file or from input, and then you have to distribute this to all other processes and show program. If the task ID is 0, then you read from standard input the number, for example, of the iteration, number of iteration in the start value, and then all other processes have to know these input values. You just can do a loop from process 0 to sending these values to all other loops, and all other task IDs have to receive these values from process 0. That would be the way to distribute it distribute the input values from the root process to all other processes. Just to show how this works. I run it, MPI run -n, say 4. Now you are asked to input the number of iterations you want to have, and then start value, say 1.0. And then you have gotten these input values, and then you send them, distribute them, and every process then can output, has the knowledge of the input value. So that's the way which to use in many applications the input values and distribute them. And what you should do now is just to use the broadcast function of MPI to do the same thing, not just send, receive, but do the broadcast. This then modifies this program using the broadcast function. This, you should try it in 5 minutes, and then we will go on. This is the question, do we need a tag for the messages to broadcast? I think it's not necessary because, as I said, the broadcast is a collective operation, which has to involve all processes. And so there's no ambiguity in the message which has been sent. It must be the same message you don't need a tag to identify the message, because all processes have to participate in the same broadcast operation. There's no parameter no argument in the coding sequence for the tag, for this type of operation, for this type of collective operation. Okay, I think I will continue and proceed to the next example, which is the gathering of data, which is a very common operation needed in many applications. So the problem is, if you have different tasks, some values produced, and you want to have these values available on all other tasks too. So you have to gather the data from all tasks to a long vector which is available to all tasks, where the pieces come from all the different tasks. So this is a gathering operation. And we have a global array, a global vector array of one dimension, global vector which will have n elements, and in NP, number of process intervals. So this global vector consists of pieces with of lengths depending on the length of the local pieces to be collected. And have to store these values of the number of elements on each process in a vector of size np. So the number of the counts of elements on each process will be stored, the number you have to collect in the counts array. When the start index of these pieces in the global array will be collected in a vector of start indices displaces. So this is displace of 0 is 0, and displace of 1 is the first element which comes from process 1, and so on. And the total length, of course, of the global vector will be n, and is the sum of all these counts, and the counts themselves can be calculated from the difference of the displacements. And in the example which we will treat, we have the following picture. We will have local vectors of length IP plus 3, so they have different lengths. The displacement on process 0 is 0, and the displacements on the different process, on the next process, will be the displacement in the process in the left plus 3 plus IP minus 1. If you do this loop with IP from 1 to NP, then the local process has the task ID IP minus 1. And the count will be the difference between these two displacements. And the total length will be the displacement value NP, which is the element NP of this displacement vector. And we will initialize this the local vectors in such a way that the global vector just has the numbers from 1 to n as argument. It's written here in the local vectors have to be initialized in this way, then the total vector will have just the indices as argument. And we want to do this gather operation, and I show you the solution send and receive. So with the point-to-point functions of MPI, collect, send, receive. This is a way to collect this data without the collective operations of MPI. So just do it with this point-to-point communication. You have here define these displacements and count values in a way I described, that every process has the number of elements 3 plus its own process ID. Then I initialize the local pieces in this way as I described. And then I write this on output that we can see which values every process has. And then I use the buffered send to collect all these values on process 0. Every process sends its local vectors to all other processes with a bsend, and sends to the process IP, does it to all other processes. And it does so its local vector with a number of elements corresponding to its local part, which is count of my ID. And then every process stores the parts received from other vectors in the place of its global vector at the beginning at the place displacements of IP. So every process, the sum over from 0 to all number of processes, the total number of processes, and it receives a number of counts of IP, and this writes them in its global vector at the correct displacement, starting from the correct displacements. Then it has you can detach the buffer, and you see the reason why I use the buffered send is because every process writes to every process, so every process also sends to himself. This would be a blocking if you have a send receive of a process to the if you would have a synchronous send of a process to himself, it would give a deadlock. But you do a buffered send, then of course it will be non-blocking on the sending side. So let me show what the program does. I run this for the 3 processes. You see the output on process 0. I have 3 values in the local array. On process 1 I have 4, and in the process 2 I have 5 values, and the values are just consecutive numbers. And after the collecting the results, all processes have the same global vector, which elements of numbering from 0, the value of the elements is numbering from 0 to 11. And if I do it for 4 processes, we will have similar picture. And you see again here the output from the different processes don't occur in the natural order, but they occur just in the order the processes are working, which we cannot say beforehand, because other people are also using this course, and so the temporal order is not prescribed and it's not deterministic. Anyhow, you see every process has the same global vector containing all the local parts, starting with the values from 0 to 17. Okay. Now, we could do this in several ways to gathering. You could do it. You could do it by broadcasting. That mean that you copy every task. You copy the local array to the place in the global array where it belongs. So every process copies the local part into its global vector. So this would be copied locally in this place and copying this in this place. Then you could do a broadcast, so that process 0 broadcasts this way to all other processes. Task 1 broadcasts this part to other processes, and this and task 2 broadcasts this part to all other processes. So that would also be a possible way to do this gathering. And this is done in the, you could do it as an exercise. I think I will skip this, and you can look up the solution in the MPI course solution files. I just want to put onto the gather method to gathering this with the functions which are provided in MPI for this purposes explicitly. So you can collect all this data with a gather vector. You have the counts and the displacements arrays already defined. So you can just call the gather vector where you send the local parts, with every process sends its local part with the number of elements contained in this local part, which is count of my ID. And then you send it and receive the global part, and you have to give as argument also the counts array and the displacements array. Then this would be gather all the local parts on the root process 0, and then you have to broadcast this global vector to all other processes with a broadcast from root 0. And of course you can combine these two operations just by an all gather vector, by calling MPI all gather vector with the same arguments here, except the root value. Then every process will receive all the values in the global vector. So I think I will show this to you, and you can. I will show you the solution for this. It's again in the solution directory. Select together. So the just to if you have defined the local parts and you have defined the displacement and the count arrays, and you just then call this MPI gather vector, and then you broadcast it, or you just write directly the altogether function of MPI. You can try this program on your own. Okay, this was a demonstration how the collective operations simplify the task of gathering data from all processes to a common global way. So we will need later on in the application. Okay. One more example for using the collective operations is if you want to signal an error to application. So you have an application with many processes, and all processes do some work, and if in one process there will be an error in executing some part, which will give you an error index, then you would not like the other processes to continue their work, because your result will not be meaningful if one process is failing. It'd be a good way to signal to all processes if an error has occurred in one process, and then to stop all processes. So this is simulated in this program rexit. I show now. So this rexit contains a loop over variable IL, which is increased from 0 to the maximal value, which I got as an input. Excuse me. Then this work will produce an exit an exit argument ix, and this can be 0 or non-zero. And if it's non-zero, then it signals that the work program has produced an error. If it's less than 0. So the work program is just a very simple one. it produces no error usually, but if the argument IW is plus the task ID of the process executing this process is larger than 10, then it signals an error, just to simulate some error, this function of this routine. And the error does occur not on all processes, but only on the process where the input value IW plus the ID of the process is larger than 10. So you will get here, you increase the input value step by step, and at some point, one of the processes will produce an error, which is an IX which is smaller than 0. So in each step, you control whether one of the processes has already produced an error by using a global reduction operation with a minimum. So you look for the minimum of all the IX arguments and put the minimum in the value IX global. Then you broadcast this value, the global error exit, to all processes, and then all processes know whether at one process the global error exit value is less than 0. And if it's less than 0, then they all will stop. So if one process produced an error exit less than 0, then all will know and all will stop in this case. So that's a way to control execution. If one process has an error in its execution, then all other processes will stop also. So you run minus N5 by maximal value of the input for the subroutine, say 3, then no error exit, no error will occur because the IW3 plus the maximal number of processes is less than 10. I now take a larger number. Okay, then still it's now if I have the maximal value of IW equal to 7, then I will have an error exit on process number 4, because then 4 plus 7 is larger than 10. So it will produce, and every other case, the largest value 7 plus the ID is less or equal to 10, so I will have no error, but the last process will produce an error, and all other processes are signaled and will stop with the error, will stop because of the error exit. Okay, that was this example. Now I give you a simple problem, just to generate a program to calculate the numbers, the sum of numbers from 1 to n, and to do this in parallel. I have given you a skeleton for this, to do it in a serial way, and you should do the same thing now in parallel by distributing the total sum into partial sums on each process, and then use the reduce operation with a sum operation, collect all the partial sums to the total sum. So you should modify the program in sum and to parallelize it by using this MPI reduce function. I will give you 10 minutes for this assignment. You might remember yesterday we had the integration program for determining the value of pi, where we had to sum the strip values from the values from 1 to n. So it's very similar, just you don't have to sum the strip values, but you have to sum the numbers 1 to n. So it's the same way to do this, and in addition you can directly use now the reduce function to do this sum over the local results. I will 10 minutes for doing this this calculation of the numbers of 1 to n. By the way, you know beforehand what would be the result. So the sum of numbers from 1 to n is equal to n times n plus 1 divided by 2. And I think this is the last, oh no, it's not the last one. So we will, in 10 minutes, I will discuss the result with you. Trying to do it, you can do it later, but I want to continue with one last assignment, which would be to modify the procedure we had in the parallel evaluation of the integral for the determining of pi, where we had to add up all the local results, which is very similar to this last assignment. So you could modify this step in this program and using the reduce operation. So that would be a practical application of this method, of this MPI method reduce. But now I will come to the next point. My course concerning the applications, and for this I have to start a new presentation. This presentation has been loaded. Okay. And yesterday we had the approximate calculation of pi. Now we want to determine the largest eigenvalue of a matrix, which I have to So this is a problem which is rather mathematically just to determine the largest eigenvalue of a symmetric matrix. So I just will describe it here very fast. And if you are not mathematically minded, so you might skip this explanation. We will see that just one operation is important in this respect, that the matrix, the multiplication of a matrix by a vector. The problem is that every symmetric matrix has a number of eigenvalues. That means that if you eigenvalue is a vector which is which when multiplied by the matrix reproduces a vector with some constant, which is called the eigenvalue. And every symmetric matrix of size n by n will have n eigenvalues. And now we assume that these eigenvalues are different, and one eigenvalue is the largest. And if I use any start vector, any vector which has a linear combination of the eigenvalues with some coefficient, and then I apply the matrix product n times to this start vector, then I will project out the largest eigenvalue by the nth power of the largest eigenvalue is multiplied by the eigenvector corresponding to the largest eigenvalue, and all the other eigenvectors are multiplied by a number which is the highest eigenvalue divided by the largest eigenvalue to the power of n, and this number is always smaller than 1 according to this assumption that the largest eigenvalue is larger than the next large eigenvalue. So this is smaller than 1, so the power n, this number to the power n will get smaller and smaller. So if n goes to infinity, you project out just the largest eigenvector. And if you do this and divide the power n plus 1 of the matrix times x divided by the power n, you just take the first element, and this will just give in the limit n to infinity the largest eigenvalue. So this is the way you multiply the input vector x again and again with the matrix, and divide the first element of this result by the first element of the last multiplication, then you will get a better and better approximation to the largest eigenvalue. That's in short the explanation for this Ritz method to calculate the largest eigenvalue. So, really to get this working on the computer, you have an algorithm, just you have to initialize some symmetric matrix and take some start vector with first element equal to 1, and then you loop, multiply the matrix by this vector, input vector x, and you call the new vector also x, and then you get a first approximation of the eigenvalue, which is got the first element of x. And then you rescale the input vector by this approximation. Then the new input vector will again have the first element equal to 1. And then you put it again in this loop, multiplied by x by a, and do this in a loop, and in any instant, in any loop repetition, the eigenvalue, the value lambda will become nearer and nearer to the largest eigenvalue. So the most important operation for this algorithm is just the matrix vector multiplication. Let's look at this in more detail. What is the matrix vector multiplication? Just if you have an input vector of length n and a matrix of size n by n with n columns, or each column or each n rows, each row has the same length of n. So this is the rows, and then the result vector will be composed just one element of the result vector will just be the product of this row times the same input vector x. Scalar product of just written here. So the ith element of the result is the sum for all these elements of the of the ith row. Every element of the ith row is multiplied by the element of the input vector. This is a matrix vector multiplication. So now the goal is to do this matrix vector multiplication in parallel with many processes. Now, how is this done? A way to do it is just to partition the input matrix into column blocks, and every process will deal with one column block of the input matrix, and to partition also the input vector in pieces, and one piece is residing on every process. So you have the situation that the global matrix is distributed in column block wise to all processes. All process will contain a different column block of the total matrix, and all processes will contain a different piece of the input vector. This is discriminated by the color in this picture with three processes. Every process has the number of columns is total number divided by the number of processes if n is a multiple of np. Otherwise, the last process will contain a smaller number of columns. And also the number of pieces of the input vector belonging to each process is n log equal to n over np. Again, n log may be smaller for the last process if the total number n is not divisible by np. Now, how do we know the multiplication in this case? See, to get on process 0 here, one element of the result vector, you would have to multiply your local parts with your local part of the row with the local part of the input vector. Okay, that you can do on the process 0. But you also need to add the multiplication of the parts of the row of the matrix belonging to the next process times the input part of the next process, and so on. So what you can do on process 0 locally is just to calculate this part of the row row which is smaller, which is has the size of the number of columns times the input vector here. You can do in the first step on all processes just the multiplication of this column, the column block times the input part of the local input part, and get a result vector, which of course has the length of the total number of rows of this column block. This you can do on every process, and then you have to add these local results, because the sum of all these local results, of course, will be the total result. So you have to add these local results, the first part of these local results on the process 0 to get the full answer of the result vector corresponding to process 0, and on process 1 you have to add the corresponding second part of all partial results to get the total result of this section and on process 0, and on process 2 again you have to add the partial results on each process, the last parts of the partial results. We have to do this 2 steps, just to the matrix vector multiplication, not of the full matrix, but of the column block matrix times the part of the input vector. And then you have to add the partial results on all processes, to get the total result corresponding to every process. So the structure of the program then will be which is called Ritz this column, because it's a way to distribute the matrix column wise. You have to have an input. You give the number of rows and columns you want to have. Then you have to initialize matrix you want to eigenvalue you want to calculate. Then you have to distribute the local column blocks to all the processes. And then you have to initialize the input vector, vector path on all processes. Then you do this loop. You calculate a matrix vector multiplication of the column block matrix times the local part of the input vector and get a partial result. The length of the length n of the total length of the number of rows, and then you have to sum these local results of all processes to a global result belonging to each process. And then you have to extract the observation of the eigenvalue as the first element of the resulted total vector, which is here. But this is, of course, the first element will reside on process 0, and every process has to know this approximation, so you have to distribute it and rescale all your local inputs by this approximate eigenvalue. Then you can go back to here. You have a new input vector xl, x local, and you have to multiply it by the matrix. Okay. What do we have to do to program this algorithm? First thing is we have to decide how to distribute the matrix. That means we have to decide how many columns will reside on any process. Okay. So we define a vector first index. The subroutine, we define a vector first index, which indicates which will be the first index of the column in each process. And we do this just by saying the local number of columns will be the integer part of n plus n proc minus 1 over n proc. So that the first index will always be we have the first index on process 0 will be 0, and then the next will be incremented always by the number of nl. But if n is not divisible by n proc, then we will have the sum be first index IP, also minus 1 plus nl for the last process will be larger than n, so we have to take just the minimum of these two numbers. So this the n local for the last process may be smaller than nl. This is the most simple way to distribute the rows, the columns, the n columns on nproc processes. Then next we have to distribute the matrix. The global matrix A resides only on processor 0, and then we have to send the first NL columns to the processor 0 itself, to the local array, to the local matrix. And the next NL rows we have to distribute, we have to send to the processor 1 and so on. So how can this be done? The subroutine distribute list matrix call block, which arguments the dimensions of the global matrix A, which is m by n, but we will always have symmetric matrices, so m will be equal to n. The program is written in a more general way. So what do we have to do? Let me see again here. We have to send all the first NL columns of this matrix to another place in memory in the process 0. But a matrix of size n by n in Fortran will be stored column-wise. So if we start in memory, we have the elements of the first row, the elements of the first column will be followed directly by the elements of the second column and so on. So all these values are stored in memory contiguously. We just have to send the contiguous amount of memory which is starting from here, and then we take the number of elements would be the number of columns we want to distribute times the size of one column. So it's n by nl. So we just have to do a send of n times nl elements to process 0, and then starting at this address, we have to send from process 0 n times nl elements to process 1, and process 1 will store them locally in its local column matrix starting at column 0. So process 0 just here calculates the number of, it will send part of its the global matrix which is residing on process 0 will send the number of elements to process IP, which is the size n, the length of a column, times the number of columns to be sent, which is first index IP plus 1 minus first index of IP. And these values will start in the global matrix on process 0 at the place at the address 1 plus m times first index of IP. Because this would be the address of this one is just skipping the first n times first index of 0 times elements. So you would start here. You see, in Fortran, it's all because Fortran counts the indices of matrices starting from 1, and these are defined as starting from first index from counts from 0, so I have to add always 1 to this address. Then I have the address where which part, which place the columns to be sent have to start, which is IA. So I send elements starting from the address A of IA, and then the number of elements is just again m times the difference of the first indices. So these are sent by process 0. They are received on all processes just in their local part, starting at the address 1 of the local matrix. And you see, I used here the I receive because I have also the sending of the process 0 to itself. So, and if I didn't use the I receive, I would have a blocking. So if I use the receive directly, I would have a blocking situation. So I use I receive, and then I have to call the wait for the communication have completed with the request handle, which has been produced here in the I receive. So that's the way to distribute a matrix. One possibility. So let me show just how this works. I will come in a moment to the second part of the parallelization, which would be the sum of the partial results. But I just want to show the result of the program, how it's running. I switch to the directory. See, I have one program which is just called ritz.f, which is the sequential version, just to check that everything is all right. And the algorithm is just as I described. We have to input the size of the matrix n. Then you have to initialize the input matrix whose eigenvalue you have, whose largest eigenvalue you want to determine. And I do this in a way that the matrix is symmetric. So, and you see, I store this matrix in Fortran not as a two-dimensional, but a one-dimensional array. And so I have to do this indices in a way that the first index I is running fastest, and the second index is just incrementing with an increment n if j is augmented by 1. So that means that all the columns indices by I are written one after the other in memory. You see here I use all, if j is smaller than I use this value. And this is the matrix is just the sum of indices divided by the index, and here I assure that the matrix is symmetric, so I have the symmetric part defined just by extension I and j. Now I initialize the starting vector with setting all elements equal to 1. Then I have the eigenvalue, the approximation to the eigenvalue is just equal to x is the first element of the input vector. And then I call in a loop the matrix vector multiplication, which is here the input matrix size n by n, and the input vector, and y is the result. So I have the new approximation will be just the first element of the result vector. And I look to the difference between the two, the relative difference, and if this difference is small enough, then I stop, then I have a good approximation. And then I have to rescale the input vector, so the new input vector will be just the result vector divided by the approximate eigenvalue. And then I set the old eigenvalue equal to the new eigenvalue in order to be able to decide whether the result is small enough. Let's see. Way of this sequential program, and I have a make file with three different programs, the sequential program and the program with column distribution matrix and the row distribution matrix. We will come to this later, but for now I will just make the sequential program. Okay, I have here in this, I have as a compiler the Intel compiler, so I have to load, I could just choose the Open MPI compiler by using the MPI fort instead of the MPI fort as a compiler. So it's done. I run -n1. Name of the executable is .exe. I'm asked how large the matrix should be. I choose a 1000 by 1000 matrix, and you see the iteration goes over 14 loops, 14 loop iterations, and the error becomes smaller and smaller, and the final value is 1530 and so on. You see the speed would be, in this case, is 400 megaflops. Okay. Now, if I do the same, I want to parallelize it. One point, I compiled this also with the MPI compiler in order to use the MPI timing routine and to have the time for this operation and to get the megaflops. So I have to use some timing, and I use the MPI timing. Therefore, I have to use the MPI compiler and run it on one process. Otherwise, I could just have just execute the executable without MPI run. I had compiled it with a normal Fortran compiler, but then I could not have used the MPI W time function. So now let's see what happens if I compile, if I make the column distribution program. And again, I can run it on one process. And again, I choose the number, the size of 1000. Okay, I don't give now all the intermediate steps in every loop, but just the end result, which is the same number of for the approximation. And I record here also the computing time and the communication time. I will show you later. The communication time comes from the collecting the data, and the speed is the same. And if I use two processors, same. I get the same value for the approximate eigenvalue, but then the computing time is reduced, but the communication time, because now I have to communicate between two processes, is larger than if I didn't have any communication. And if I do it on 4, again, the speed is nearly doubled, and you see the communication time. Well, it's even smaller here. It should be larger because I have more processes, but that's also the non-deterministic behavior of a multi-user system. Okay. But now let's discuss how we do the reduction of the result on the local parts of the execution. So we have discussed the distribution of the global matrix. This will give rise to an exercise later on. But now I want to just discuss the reduction of the vector. You saw I explained that every process will produce a result of the matrix vector multiplication resulting from the multiplication of a part of the input vector times column block of the matrix. And I have to add all these partial results to one total result. I could do by reducing these three result vectors on the root vector, on the zeros root process, and then I could send the parts of the results of the total result vector belonging to the different processes. So I would I would keep just the first part on the process 0 because it belongs there. The second part I would send to process 1, and the third part to process 2, and so on. That would be one way to collect all the partial results to a total result, and then to be able to go to the next iteration, because then I have in the local part the full result. Because this could be done faster or more compactly by using the MPI reduced scatter, because here I do nothing but have two steps. I do the reduction on processor 0, and then I scatter the value to all processors, which is here in 2 steps. Step and then the send and receive step, but I could do the send and receive implicitly by a reduce scatter operation, which I explained yesterday. So, you have to include into the scatter function not only the send buffer of the elements to be reduced, also the counts, how many of these elements, of the result elements, should be placed on the various processes. And this would be an exercise for you to do to modify this program by using just one call to MPI reduce scatter. And this would be just to define this counts array, which tells you how many of the result elements should reside on every process, and this would just be the counts on process I, should be first index of I plus 1 minus first index of I, and then you can just replace the call to MPI call to this routine. Just you can it's composed of two parts of the MPI reduce and send and receive. You can just replace by one call to MPI reduce scatter, where you include the counts. Then automatically the corresponding parts of the reduced value of y will be put in the correct places in the local input parts. Okay. So much for the distribution of the matrix in a row, in the column wise. But why not? We could also choose to distribute the matrix in a row-wise fashion, so that every process contains a block of rows of the total matrix. Again, it will contain a part of the input vector, the same size as the number of rows it contains. Now, how do we then do the multiplication? See here, if you have the process 0, at the beginning you have only one part of the input vector. So in order to calculate an element of the result, you have to multiply a row residing on the local process times the full input vector. So before calculating a result, you have to fetch from the other processes the other parts of the input vector. And you can calculate in one step all the results corresponding to your process by multiplying your own rows you have in your column, in your row block, by the total input vector which you have collected before. What you have to do is, if in any process you have to combine all the local parts of the input vector to a total input vector. And then you can use this total input vector, which is the same on every process, of course, to produce the different parts of the result vector using the rows you store locally. That's a way to do this in parallel, or parallel matrix vector multiplication with a row-wise distribution. Again, the program has the same structure. You have to distribute the rows of the global matrix to the local matrix and the local parts in every process. And then you have to collect all the input parts of all processes to a global input vector, which will be the same on each process. And then you can do the multiplication with a large input vector and produce a local part of the result vector using this local row block. Again, you have to determine the approximation of the eigenvalue by using the first value, which will be residing on process 0, and you have to distribute this and rescale as a new input vector. You have the result vector here times rescaled with the approximate eigenvalue. So it's the same here. You aggregate, but now we have to careful to do this distribution of the full matrix to all the local parts, the local row blocks, to the different processes. Why is this more difficult? Because in memory all the columns are stored consecutively. If you want to copy to send this row block, you have to combine different parts which are not consecutively in memory in the process 0. So the parts you want to distribute are not contiguous in memory in the zeros processor. So you have to do something. Let me show it here again. You have a global matrix A of size n by n, and you want to copy the rows, number of rows into a local matrix of size n by nl times n. So that here in the local matrix, all these small columns of size nl are consecutively. The n small columns, local columns, are consecutively in the local memory. But in the global memory, they are not consecutively in memory, but they have a stride. So the difference in address here will be by have a difference of n in memory. What you have to do, and you must remember the send and receive operations of MPI just send contiguous pieces of memory, n elements contiguously stored in memory. So you have, if you want to send this data to other process, you first have to collect them into contiguous memory space. What you do is you just copy these values on process 0 into contiguous space. This way that you have this is the matrix elements. The matrix element you want to collect are sum over I over 1 to NL, not to N, but only NL, to the local size number of rows, and starting at some address, which is the address is the first index for the process IP, and then sum over all rows from 1 to N, in this way that you run first with the column index and then with the row index. So this will collect these rows in a contiguous memory space in IL. Then you can send this contiguous memory content in one call of send. Just the number of elements to send is then n by nl from this process 0, which I have collected in the local array AL, the local matrix AL, you can send to the process IP. You can use just the same local matrix AL on process 0 if you start sending something to the other process, and the last time you have to collect the first rows, and then they are residing just in the local place you want to have. So you can use the same local memory space for this compressing of the rows to a contiguous space and then sending them, and in the last step you fill them with the first rows you will need on process 0. So that's written here again on process 0. So collect the row block, contiguous memory in the local matrix, local array AL, and then you send this AL from process 0 to process IP. And you proceed in reverse order so that ending you will have the AL which you need on process 0 containing its proper matrix values, row block. So this is a way this can be done. On process 0, you just determine, you do a loop over all processes, starting from process nproc -1, reversely to process 0, and you determine how many rows you want to distribute to send, which is just first index IP plus 1 minus first index IP, and the number of elements you want to communicate is just n times the size of the column in this row block. Number of columns in this row block. Excuse me, the size of the rows in the row block of NL rows. Then do this copy as I showed in the slide, in the previous slide. And then if IP is greater than 1, you send these values from your local space AL to the address AL in process IP. This is done for IP equals 0, and if you are not, if your task ID is larger than 0, then you have received this number of elements n times first index of my IP plus 1 minus first index of my ID, and you will receive this number of elements from process 0. So far. Now it's rather cumbersome to do this two-step way of distributing the column blocks. You have the first step, you have to collect and compress the elements into a contiguous space. You compress all the columns, all the rows into a contiguous space, and then you can send this data from this new space to all the processes. And now MPI provides a measure to make this easier. Just you can find data types which are not contiguous in memory. You can define a data type which is just the structure you need, which is the function MPI type vector. You just define type consisting of n pieces. Each piece will have the block length of the size of this column, and you give the stride which these pieces are apart in memory, which is just the first dimension of this matrix. We have these three characteristic values for this data type, which is the number of pieces you want to concatenate, and you have the size of the pieces, and you have the stride these pieces are apart in the memory. In this data type you give a name which the elements of the old data, the matrix elements have the old type, which would be double precision in our case, and the new type you give some name you want. And this would be just an integer in Fortran. Okay. Then you can use this new type to do the communication of the data without collecting them explicitly, but because the system knows which elements are involved in for this element of this type. What you have to do is on the process 0, you define a new type, say row block. This program, the MPI program, MPI type vector. Then you have to activate it by commit this new type. Then you can send process 0 just this beginning from some address, which would be the address of the global matrix at the first index IP +1, where the rows will start, and then you send one element of this new type, which contains all the data, send them to IP, to the process IP, and then you can you have to free this new data type. And of course, on the receiving side, all other processes just have to receive their this data, send it with this type, just in a local array contiguously. Okay, and I have this. Let me see. In our folder with all these programs. I have here this matrix row block. Which, as I explained, is a first version where I have to collect explicitly all the data from the global matrix on process 0 to a contiguous space in a local matrix, and then I have to send this contiguous memory space with this number of elements to process IP, and in IP on process IP other processes, if my ID is not equal to 0, but is some other value, my ID, then I just have to receive this from the process 0 with the number of elements I need, which is n times first index my ID plus 1. So as I explained. And the other way you can find in the solutions, just matrix O. Okay. It's much simpler to program. Just receive the data. On every process you have to receive the data in your local space for the row blocks, RL, and the number of elements you have to receive is just the number of the size of a row times the number of rows, which is this. First index my ID plus 1 minus first ID my ID. And on process 0, you just have to define this new vector type, data type, vector n and l m is in this case equal to n. And you give it a name row block. And then you commit this, and then you send this from the address corresponding to the first row belonging to this row block. You send one element of this new data type. And again, I have here used the I receive because I also send this data type to my from process 0 to process 0. So I do the copy implicit by this vector type mechanism, by this by using this data type of row block also on processor 0. So I don't have to explicitly copy it. It's just done by sending this vector type, this row block type data to process 0 to myself. Then I do it with an I receive, and so it's non-blocking, and I have to call the MPI wait to guarantee that the process has been finished. Okay. Well, the second part of in this case, you have to collect all the result vectors into a total result vector, and this is the same way we discussed in the exercises for the collective communication. It's the same procedure. You can do it in various ways I described there, so I don't want to go into it. Same as now what you could do, use to see how efficient the parallelization proceeds. Let's see the part of the communication here takes some time. Gathering data takes some time, and the time will be the longer, the more tasks are involved. Then you can compare this time with the time for the computation of the matrix vector multiplication. So, and the total speed, of course, the speed will combine the time for communication and the time for with the calculations. And so you can see if you increase the number of processes to this calculation for different sizes of the matrix, you will end up as a speed increasing, and the speed will not increase proportional to the number of processes, but you will lose some efficiency. So you could test just by using for certain for certain size of the matrix, you increase the number of the processes used, and you can look where the efficiency becomes smaller than 1/2. So if you start with one process, you get a megaflops number, and then you do it on 2 processes, and you compare the time on one process by the number of processes times the time on 2 processes, and if this is smaller than 1, you see that the efficiency is smaller than 1, and you can increase the number of processes and compare this time on one process divided by the time on n processes times n number of processes. When will it get smaller than 1/2? At some time it will the efficiency will be smaller and smaller. So the program time, I see. The program, you can see the program time yourself. Also, you can copy all the program results from my folder, but I will show you the program time one more. So, is this the program you want to see? In any case, you can look yourself on this place. On the disk place, you can copy this from my home directory. The permission is there to copy this data files. Okay. So that would be perhaps interesting to see how at larger n you will have an efficiency drop only at larger sizes, at larger number of processes. You can do this in your spare time, because now I want to switch to the last application I want to show you. This is diffusion application, but before I do this, we'll make a short break of say 5 minutes to recreate ourselves. I will continue at 11:22. Fusion equation is a physical equation describing the behavior of materials as some container as heat is dissipated, or where some mixture is expanding, or so on. All this is described by the fusion equation, and the type of this equation is the following: that you have some substance in your domain, which every point of your domain X you have a value for concentration or temperature, and this value will change with time, and the diffusion equation describes the changing of this property in the material. So the time derivative, so the time evolution in time is proportional to this delta is a Laplace operator. This is a second derivative with respect to the space. So the time evolution is proportional to the difference of the property in space, the second derivative, plus some input value, some source which you in the system. And I will describe this simplest way, kind of this equation in a two-dimensional domain, where x is in a square size 1, and you have to solve this equation. You have to give start values, initial values, and boundary values. So you have to prescribe the value of the property at time 0 in all the domain, and you have to prescribe the property at the boundaries of the domain at all times. So, so you have to know the temperature at the beginning, and you have to know the temperature at all times, the fixed temperature at the boundary. So for 1 equals 0 and 1, and 2 equals 2 and 1. Then one can solve this equation. Well, for us, using computers, we cannot solve continuous equations. We have to discretize this, and discretization means that you put points on your domain, grid points, and then you consider the value of the property only at the grid points. So we approximate the interval from 1 to 0 by n points, by n plus 2 points, where the point 0 and point n plus 1 are the boundary points, and the inner points, I have n inner points in each directions, which will change. But at the boundary, the values will not change because I have fixed boundary values. So the temperature or whatever property you consider will be stored in a two-dimensional array, and this is indexed by two indices corresponding to the grid points, I1, I2, and then you can discretize this equation in space and time. You have a small time step, a small distance between the grid points, and you say you can calculate the value at the next time step from the values at the previous time step by this equation. Two time step at one point in the grid, the value of the property of the temperature will be proportional to the old value plus the average of the property at the neighboring values. That's the way, because this is a differentiation in time, in space, in this translate into the average of the values in neighboring points. And you have to prescribe the values at all points at some time at the time zero. The values at the beginning, and then you have to prescribe boundary values at all points at the boundary, which is these points second dimension equal to zero and all indices of the boundary. In the picture we have the grid with a number of points, and we have the inner points where the temperature will change, and we have the boundary points where the temperature is fixed by some external container or something which keeps the temperature fixed at the. So this is the setup, and we want to calculate the development of the property of the temperature in time using this fusion equation, discretization. Now, this algorithm then is very simple. We have an input where we, as I had to mention here, if you calculate the new value of the temperature of the property, you have to use the old value and the average, but they are multiplied by some constants S and R, and they are calculated from via the discretization from this physical constant rho and C and K, which are theory constants. So in any case, the theory of discretization says that this discretization only works if the R value is smaller than 1/4. That one can prove in applied mathematics. So I have to prescribe some value of R, indicating the properties of the material I want to describe. And then I have to say how many time steps I want to calculate and the size of the number of grid points, the resolution of the grid, which is the number of n of points in every dimension. Then I have to fix the initialization of the whole matrix in the inner points, and I have to fix the boundary points by prescribing the value at the boundary, and then I have to do a loop, and I have the old values, and with this formula from before, I calculate the values, the new values at all the inner points. And then I can the same and take the new values as input and override the new values. So I have just in the loop I have 2 time steps, and I end up again with storing the new values in the array U. So I have 2 arrays, one U and one UN, and I do a flip-flop between the two with an update, and I end up with a new temperature after 2 steps in the same memory plane. So I think, yeah, and the update is just done in a subroutine side schritt, which gives the number of points in both directions of the grid, and the old values are stored in A, the new values in U. And I must apologize if you have copied this presentation slides yesterday, I had a mistake here and a different order of A and U, but now it should be in this way. I misplaced the values of A and U in the old. Right. This is the correct way to write it. So, and the Zeitschritt routine calculates the new values in the array U for for rows and columns 1, 2, and 2. And yeah, it's called the new temperature within the grid, which means the rows 1, 2, and 2. And it uses for this all rows starting from the boundary rows. This from A. So we will need this later on, that you use all the rows, including the boundary rows, to calculate the inner values of the new temperature. We have this program, and I will just show how this runs. I have to switch to the directory Wärmeleitung. Again, I have a make file here. So see. Again, I have the compiler, so I changed the MPI implementation to the Intel. The modules for the Intel I, instead of modifying the make file. So it's compiled, and input values I can change by reading I have put into an input file. Here l.input. So I read the number of time steps, the size of the matrix, and the value of R. Then I do this with one process because it's sequential. I have to read this input file. So I redirect. So in one process, I also displays the values at the inner points. And you see, I give the average temperature. I display inner points, not all inner points, but also points in some distance, so that they cover. They can display them just on my screen here. So you see the boundary values I have chosen equal to 9, and the initial value equal to 1. So after 300 time steps in the middle of the domain, the temperature has not yet changed, but from the boundary, the temperature is rising in time. So, and the speed is 8 gigaflops. Okay. This is the layout of the program. And now we go on to discuss the parallelization. Now, how to parallelize this? Just by putting the grid, partition the grid into pieces, into strips, and put one strip to every process. So with 3 processes, I have here my grid with inner points and boundary points. Boundary points in these lines, and inside the lines are the inner points. And you see immediately what happens if I distribute the domain to into different processes. That in this, if I want to update the temperature on process 0, I need the values in process 0, but on the boundary, I need also the values from the neighboring strip. Before I can do the update, I have to somehow to transfer the values from the neighboring processor. The first row from the neighboring process, the first column from the neighboring process, I have to copy the boundary of my local strip. I have to add a halo as one says, a halo piece for my domain, where I can copy the data from the neighboring domain. So, and of course, in the leftmost domain, I have only to copy the right boundary. In the other processes, I have to copy on both sides, left and side, the boundary from the neighboring domains and so on. And on the rightmost strip, I have only to copy the left strip to the boundary. But that's after this exchange of boundary, after exchange of this halo values, I can proceed just to calculate locally the temperature update, because I have all information now available to calculate the new of the temperature. So then the algorithm would look like this. At first I have to do this exchange of boundary, which is in German Randaustausch. I have to Randaustausch of the n values in the boundary, and then I do the Zeitschritt update on my local piece, get a new local new values in the local domain, in the local strip, and then I do boundary exchange on this new value, and I do an update with the new values as input and store them in the U, so I can do this loop and again here feed the U value as new input. Again, in this loop, I have 2 time steps in the loop to end up with the values in the old place of the temperature field. Now, how this boundary exchange is done. So every process sends its first row left and receives in its 0th row from the left. And the local domain starts from with row 0 and it ends with row n local plus 1, which in 0 and and local plus 1 are the boundary rows, are the boundary. I think I mix up the row and columns because, excuse myself, I think. I think these are columns which have to be exchanged. So excuse my mistake. This must be read columns always. So, you send the first column to the left and receive the first the values for the zeros column, for the boundary column from the left. Then the NLs row will be sent to the right for the neighboring domain and to receive the values from the neighboring domain and put it in your boundary domain, which is the NL plus 1's row, column. And of course, as I showed you, the leftmost and the rightmost domain do not need to exchange boundaries to the left or to and respective to the right, because these are the fixed system boundaries. But MPI allows to unify this behavior by saying I send something to MPI proc null if there's no domain at the right side. So so you have a uniform version to do this boundary exchange. You can see it. I have and also the boundary exchange, which has 2 dimensions, and 1 and 2, and input the array, the local array of the local domain. Then I have a left neighbor, which is MID minus 1. But if I am the leftmost have the leftmost piece of domain, then my left neighbor is not existent. So I put left neighbor is MPI proc null. Same for the right neighbor is MPI plus 1. If I am the rightmost, if I have the rightmost main piece, then my right neighbor is just MPI proc null. And then I call send receive. I'm sending something to my left neighbor. This is the first column, starting at value 1. I have n1 elements to send, which is this send of 1 column. And I receive from my left neighbor just the boundary which is stored in my array at column 0. And to the right, I have the same. I send the column number 2 in 1 element, and I receive from the right neighbor values which I store in the boundary column. So let me I will show you how this works. show you at first the boundary exchange routine in full. You see my local domain is a two-dimensional domain with elements starting from 0 going to n1 plus 1 and from 0 to n2 plus 1, which so includes the boundary. The 0 and n1 plus 1 indicate the boundary values. And as I have written before, that this is just if I gave on my slide. Important to remember that the iteration of this local array must start from 0 up to n1 plus 1, 0 up to n2 plus 1, in order that it can contain also the boundary values. But the update will be done only then for the inner values. Then I can make i.f Wärmeleitung underscore MPI. I run and do executable for MPI, and again I have to read the input data, and you see get the same temperature and the same picture on one process as before. And here I also measure explicitly the time needed for the Randaustausch, for the boundary exchange, and for the update. In this case, of course, on one process I don't need the Randaustausch does nothing, because the left and right neighbor will be the MPI null. This will be changed if I use, say, 4 processes. You see now you have a non-zero time for Randaustausch, for boundary exchange, and an update time, which is of course smaller than before. Nearly a factor of 4 smaller. So you really have a increase of speed of a factor of 4, because you use now 4 processes. Well, let's do this just for 16. I hope you get the same average temperature. So this shows that the parallelization gives the same result as the serial execution of the program. Okay, now you have a typical situation that the same size of the system, the larger number of processes, just the communication time in the exchange program is nearly as long as the computation time. So you will no longer have a linear speed up, linear in the number of processes, but it will be because the total speed includes both times. So you will have a decrease in efficiency. This I would like to analyze for detail. Scaling analysis. In our application, for the heat equation, for the diffusion equation, we have for every update of the temperature, we have n square points to update, and for every update we have to do 6 operations. The additions and multiplications are just 6 operations, and this will be done on NP processors, so each processor has to do this number of operations. The processor has to transfer to its neighbors 2n numbers from the boundaries, one to n to the right, n to the left. So that makes the speed, the execution time has 2 pieces, the chemical operation time and the time for communication. So the time for doing the operations would be the number of operations times the inverse speed, the time for one operation. And then the communication takes the time, which is because I have to do to left and to the right, we have a factor of 2, twice the latency, and in every communication step we have n values to communicate with the inverse bandwidth. So we have a total speed on NP processors, the speed on one process times the number of processors, and then I have 1 over this factor. If I so the total speed is just the number of processes divided the time. So I do this, I get this formula. I have here 2 pieces, NP over n square times the latency times speed, then the time NP over n proportional to communication speed times communication speed times bandwidth over bandwidth. You see, one part is multiplied by number of processes over n square, and the other is multiplied by number of processes over n, because we have here an additional factor of n multiplying the communication time or per word. So now what we would be interested in, how many processors or cores can we use meaningfully. So say we choose a number of processes such that the number of grid points is proportional to the number of processes. So every process will have the same number of points to work on, because the number of operations per process is just n square over np, so the number of operations per processor would be proportional to alpha. When we keep alpha fixed, so we increase the number of processors proportional to n square, and if we put this in this equation, then you see np over n square is constant, but np n will be proportional to square root of np, because n is only square root of np. If I increase np more and more, and also n square increase n square any more and more, it's constant alpha, the speed will increase as some value of the some times the value on one process times the square root of the number of processes. But that's not very comfortable, because the optimal way would that the speed increases proportional to the number of processes, of course. The processor I employ, the more speed I can gain. But in this algorithm, the gain is only proportional to the square root of np. And that's very good if you want to deal with really large domains and a large number of strips, and it's not reasonable to use too large a number of for a fixed number of grid points. You cannot increase the number of processes as you would like. So this says you that this algorithm is not optimal. What could one do to improve it? Crux is that you have to communicate n data for every process. And therefore you have here the NP over n. It would be better if you only had to communicate less data, and this can be achieved by using a different composition of the different decomposition of the domain, and the solution would be to use a two-dimensional domain decomposition, because then you see the domains have the boundary not equal to the total length of a strip, but only to a smaller way. You can do this two-dimensional decomposition. The analysis would be the same as before. If you now use number of processors, which is a square, say NQ. If you have 4 processors, you would have a two-dimensional grid of processors, so NQ would be equal to 2, or if you have 9, and is it 3, so you have a number of processors which is a square, and NQ is the value of the square root of NP. So the number of words to transfer then would be transfer in 4 directions, left, right, but up and down also. So you have 4 transfers, but each transfer involves not n elements, but only n over nq elements. The square root of np is n square over square root of n square over np. Now, if you do the same analysis as before, then you have again the part from the latency, and now from the communication part, you have not np over n, but nq over n, because the size of the boundary pieces you have to transfer is only nq. Is only nq over is it's only n over nq. So, and if you do now the scaling analysis with n square proportional to the number of processes, then you can scale up. NP goes to infinity, then you will really have here some factor times the original of one process times the number of processes, because then nq over n is proportional to alpha. So this I will discuss in the last section after the break for lunch. In between, if you are interested, then determine some behavior of the operation, time for operation for different sizes of different number of processes using such a scaling size of the domain. And then you can see that this doesn't that the efficiency doesn't scale, but efficiency drops if the number of processes is increasing, even if the size of the grid is increasing. Okay. I think here I will stop to make a break and to have lunch. I invite you to come back at, say, at 13 hours. Then we will be the number of processes needed to parallelize this algorithm, and so the number I input should be smaller than the value n proc with which are just started with the MPI run command. So then I have to map the task ID, which are in my initial communicator MPI com world, which are linearly numbered from 0 to n process minus 1 to two-dimensional in the order with this with a two-component indication. So I have two coordinates for every process, 1 and 2 coordinate, and then I have to calculate the block sizes for all blocks, which are now n1 local and n2 local, and I have to initialize the blocks, and most importantly, I have to do the boundary exchange for the two-dimensional distribution. So let us start with the topology and the numbering of the processes in a two-dimensional in a grid. So if I have just say 4 processors, which are normally a flat set of numbering 0 to 3, then in 2 dimensions I have to have 4 processes with two-dimensional numbering with two values for the coordinates of the processor. So they will have the numbers 0, 0, 0, 1, 1, 0, and 0, 1, 1. And the linear numbering must be converted to a two-dimensional numbering. The first step. Now, this step will be can be done with the help of MPI structures and programs. There's one function in MPI which is called MPI cart create, means create a Cartesian grid of any dimensions. So you can call MPI Cartesian cart create with processes in the old communicator, and you give the dimension of the grid, the Cartesian grid, and the values of the number of dimensions, the values of the dimensions in an array, and then you can specify periods of this grid, which means that you can specify a period or non-period grid for each dimension. If you put in this logical array for each dimension, you can put the value true or false. If true, then this dimension will be period, so that the neighbor of the leftmost member of this in this dimension will have a neighbor which is the zeroth element in this dimension. Or it's false, and it says the leftmost has or the rightmost do not have any neighbor. And you have an argument reorder, which allows the ranks may be reordered. It means that you don't need necessarily to have this specification 0 goes to 0, 0, 1 to 1, 0, but just to have a reordering according to the physical placement of the cores, for example. Then you have to give a name for the new communicator which has the Cartesian topology. Now, after creating topology, you also can get information about the numbering of the processes in the new topology, the two-dimensional or the more dimensional numbering. Call MPI Cartesian get with the new communicator as an input, as a communicator. Again, the number of dimensions of the processor grid and the size of each dimension and the periods. Then you will get the coordinates of the calling process in this new virtual topology. So the coords as many elements as dimension as the grid has dimension. So, example, if you want to create a two-dimensional grid, you have to have this integer arrays dimension of size 2 and the task ID, two-dimensional task ID, and you have to provide the periods logical array of size of the dimension, which is 2 here. And then you initialize your MPI with MPI init, and you inquire the size, the original communicator, how many processes, and the process ID in the original linear array, linear setup of the processes. Then you have to specify the value of the two dimensions, and you specify the periods, which I put here equal to false, so the grid will not be period but period. Then I call the creation of the Cartesian grid with the old communicator, which is MPI convert. I have two dimensions, and the dimension as I have written here, periods, and I want the system to be able to reorder the linear numbering of the processes, and then I retrieve the two-dimensional numbering of this of my process. Excuse me. Here I give the name. This is the name of the new communicator, which I which I call com2d, which I have to specify as an integer. I lost one m here. You see, compared to the specification. So error here. But nevertheless, I create the grid has a new name. The virtual communicator created has a name com2d. Then I can get the my identification of the process in the context of this new grid, which is given then in the two coordinates of the MyID 2D. I can write them out. This is a way to handle the two-dimensional topology in decomposition. Now the second point is we have to handle the boundary exchange within the two-dimensional topology. I have a subroutine which as input the local piece of the domain belonging to the processor, which to the processor, the process which is calling this Randaustausch. And then I have again there this local piece of the field containing the data of the temperature, and runs from 0 to n1 plus 1 and 0 to n2 plus 1. And I have additional, we'll see why we need them, have additional memory space and arrays in the memory which are needed to data. And then it's continued. I have the parameters of my process in the initial communicator, which is com_world. Then there is a very useful program in the in MPI, which determines the neighboring values for the neighboring identification values for the processor in a Cartesian grid, which is the shift, which will give me the neighbors from my processor in the vertical and horizontal direction. The direction is indicated by this number. 0 is horizontal, 1 is vertical in 2 dimensions. And then it's a shift in with 1 unit, so it's the direct neighbor in this vertical direction. And then the shift function returns just the coordinates of the neighboring processor in this 2-dimensional grid in vertical direction. The lower and the left and the right, vertical, the lower and the upper. It should be the lower and the upper. See whether I did it correct here. So I had to place this here. It's you should call it here right, left and right for in horizontal, and horizontal direction you should call it up and lower, but that's are just names, so one will run correctly nevertheless. So this shift here is again the general calling sequence. You give the name of the communicator for the virtual topology, and you give the direction which the neighbor, the shift should be affected, and the displacement, how many steps the displacement should be encompass, and then get the rank of the source this direction, which is the direction in this direction with minus display is finished by display, and the destination is then it's augmented with the display. values. So the direction can be one of the numbers from 0 to dimensions -1, where dimensions is the dimension of the Cartesian grid. Okay. And this is the rank in the linear numbering of the processes. Therefore, can use this send receive operation now in your usual in your original communicator context, because you know the neighbor, upper and the lower neighbor, number of the neighbors in the usual communication context given by this shift function. We do the same as before, send receive in the vertical boundaries. Okay. Excuse me, the vertical boundaries, let me see in this picture. Vertical boundaries would correspond to these boundaries. So that's okay that I call them left and right. Okay, that was okay. Vertical boundaries correspond to the columns. Okay. So it's everything has been written correctly. And the vertical boundary is just a contiguous piece in the memory. The vertical boundary is just which you have to send. Is just the first inner column of your local domain, and you receive it in the first in the first in the zeros column, which contains the boundary, and you values from the neighboring process. We have to do the send receive from the left boundary, and the right boundary. So that's not different from the case with one-dimensional exchange. Well, in the other direction, the horizontal boundaries, because they have a different problem, additional problem. Go back. This picture. The horizontal boundaries, which have to be copied to the neighboring processes, to the local domain of the neighboring processes. Of course, these are rows in this domain. In the temperature field is a row, and the elements of a row are not contiguous in memory, but they are stored in memory with a stride to the size of one column. You cannot directly transmit this horizontal boundary to the values to the halo of the neighboring process. Therefore, we have to copy them before transmitting. You have to copy them to a if you copy them to a continuous memory space, which is done in Fortran by this. We copy first we copy the horizontal boundary of row 1, values from 1, 2, and 2. We copy to a contiguous space as you remember we declared in the subroutine additional arrays, linear arrays of some size, and the size must be large enough. So I didn't put here very precisely, but I gave some large number, and in a real case you have to adjust this number to the size of the rows. And okay, you have to copy the row which is not contiguous in this array A, because in this two-dimensional array the columns are contiguous but not the rows. And then you copy something from RS to your upper neighbor, and at first you determine in the upper and lower and down neighbor from in the horizontal direction with this shift function. Then you have the ID of the neighbor, upper and lower neighbor, and then you send something to the upper neighbor and you receive something from the upper neighbor, which is again in contiguous memory space. Then you have to copy this contiguous data into a row in the Harlow boundary row of your local temperature field, which is done by this the row 0 will be filled with the values received from your neighbor. The same with the lower boundary, where you the values of the row n1 to some contiguous memory space, and then you send it and receive something from your lower neighbor, which you have to copy. Okay. And of course, do the copying only if your process is not at the boundary of the process domain, because if you don't have to copy data if your process is just at the upper boundary of the domain, because then you have already the global boundary values, and these values for the neighboring process numbers already includes the case that if the process is has no upper neighbor, then this value will be set to MPI null, as we used in the one-dimensional addition. Again, here we have to do the copying only if the lower neighbor really exists. Again, as I explained, case where we had to distribute the matrix in a row-wise fashion, we also had to condense the data to be communicated into a continuous space. We can also use here a vector vector data type to construct to do this without copying. I define a vector type row, which is which has n2 elements, and each element has just one piece, and the stride of these elements in the original array is just n1 plus 2, which is the length of one column. And then I call this type row, I commit it, and then I just send and I just send the row, receive, I send one piece of row, I send beginning at this address, and I receive one piece of row starting at this address. And automatically the copying which was done explicitly here will be performed within the using this data type row. So these are the elements used for doing all this in a two-dimensional grid of processes. And then I have the code written in a complete code in directory WL2D. And I have this code only in Fortran because I didn't have time to generate C or Python versions, but you can do it, of course, if you want to other languages. You see, just show you this of codes. Seem to be okay. I somehow have difficulties to share my login window with you. Okay. how it works. I switch to this directory UL original, and I have all these things which I showed you in the program files. See, the input is so in the input now I have to give also the size of the processor grid. If the input here is in direction is 4, so I have a 4x4 processor grid, so I need 16 processors to start this. And my program, two-dimensional MPI program, is have to read these values, then have to broadcast all the input values to all processes. And then I generate my two-dimensional process grid. It's called COM2D, and I ask for the values of the two-dimensional numbering of my processes, which is put into this gray cohorts. Then I have to choose a partition of my two-dimensional domain in two-dimensional pieces. So I have to use two first index arrays in both direction one, and one will need the number of processes in one direction and the number of process columns in the other directions. Then the number of rows in both directions are, of course, the first indices in the two the processor indices in directions. Then I have to initialize all my local domains for the two-dimensional decomposition. And I declare this can declare this this new data type for the rows to be communicated. And I call this Randaustausch and so on. Okay, let's just see whether this works. I've compiled it now, and now MPI run -N16 and I have to read the input values. Okay, you get the average temperature here and speed according to the use of 16 processes, of course, is very large. And you see here the update time. The pairing is comparable to the exchange time because the system size of 400 by 400 and 16 processes, so the work to do on one process is not too much. You see here, well, I give in an output just the sizes of the local domains for the different processes. Okay. So this is a way to do a two-dimensional distribution of a domain and to parallelize two-dimensional domain. I see here's a question. Okay, let me explain this. In this case, IPU equal to 0 means this picture. If IPU is equal to 0, that means all processes in this row have the value of IPU equal to 0, because the upper neighbor, this processes is empty. All processes in this row have a neighbor, an upper neighbor which is 0, so I don't have to do anything for them. And if the AP and if I'm on this processes and I look for the AP down, then you see the lower neighbor don't exist, so I don't have to copy data from here. I think that's the reason. See, if I calculate with my MPI function the displacements of the processes, then automatically I will get, if I inquire the upper neighbor from a process in the upper row, I will get the value MPI proc null. For this, in this case, will be nothing be done, and I don't have to copy data. Hope this, yes, okay. Now one last point, which I want to demonstrate with the diffusion equation, the parallelization of this equation, is something concerning the overlap of communication and computation. Let me return to the case of a one-dimensional partition of the domain. So I say I have displayed here one domain of one process. So, I have the upper and lower boundaries are the fixed boundaries because these are the original boundaries, and I have only neighboring processes containing neighboring domains, which also reach from the bottom to the top. But within one local domain, I have columns which are the first inner domain and the last column of the inner domain, and I have the boundary, which is not inner, but it's a boundary belonging either to the global boundary or to the neighboring processor. What I have to communicate before computation, I have to communicate these. I have available the rows in this domain. I have all rows ready in my process. They are available, but I have to receive from the neighboring the columns. It must be the columns 0 and n1 plus 1. I think I should replace all row by column here. Here must be read columns. So this is the communication step, and then the computation. I compute the rows 2 up to n1 and nl minus 1. I can compute using just values which are original already in my domain, and only computing the column 1 and column nl, I need the values for my neighboring processes. So from this picture, you can see you can do the computation of columns 2 to nl minus 1. You can do before communicating the boundary values. You can do something. Can do this. Compute the new values in columns 2 to nl minus 1 before the communication has completed of the remaining value of the values in the boundary. So that means you can overlap and communication using this fact. So you can overlap communication and computation with a non-blocking communication. The way you start do non-blocking sends. Start non-blocking sends by sending the first and the NL's column to your neighbors. And then also you start two non-blocking receives to receive the data from your neighbors and be put into the boundary columns of your domain. You start non-blocking sends and non-blocking receive calls, which return immediately, and you can then start to update all temperatures in all columns. It must be read columns here. In all columns to up to NL minus 1. But of course, you can update the columns 1 and NL only after the communication of these boundary values has completed. So you have to put a wait for the completion in this place, and then you can update the two last columns. Okay, that's a way to do it in a subroutine. Which was called boundary Randaustausch. I now call it immediate exchange using the non-blocking sends and receives. And the subroutine has as an argument the request needed, the request handles needed for this you have 4 send and receive operations, so you need 4 request handles. For every of these I send and I receive, I use a different request handle, of course. And then I do the I send, and for the left and the right boundary, receive from the right and from the left neighbor. And this would replace then the Randaustausch program in the original program for the Wärmeleitung. Then the time step, then well, the time step is I use a more general routine for the Zeitschritt or time step, which tells me which columns should be updated, because I must differentiate between columns 1 and the last column NL and the rest of the columns. So I have in this time step, I have I do the columns only starting from J2A to J2E, from Anfang to Ende. And I do not update all columns, but only the columns indicated in the calling sequence here. Okay, and then the program would run in the following way. I have the update loop, and I call the exchange of the boundary values program, which gives me some request handles. And then I do a time step, but I do the time step not for all columns, but only columns 2 to NL-1. Then I have to wait until the exchange procedure has finished with a wait call, and there's a wait call to we had before only the MPI wait if we had one request, but we can also wait for the completion of several requests with a wait all. Then this will block until all the requests contained in this array have been finished. Then after this, I'm sure that also the boundary have arrived in my in my old temperature field, and then I can go on to the time step also for the last for the first column. So I do the time step from 1 to 1, and then for the rightmost column, which is NL. I do the time step for NL. Then I change A and Q, and that's sim. And in this way, you can overlap the update of the inner columns in your domain and the communication of the boundary columns from the neighboring domains. And depending on your computer system, that will be beneficial if the communication system has own hardware to do it, and doesn't involve then the CPU itself. So then it will be a bit faster than without this overlapping. See, I think The code for this overlapping two-dimensional is in the directory Wärmeleitung under the names of heat MPI, time step and I exchange. So I think this is all I can tell you today about applications of the MPI parallelization in these examples, and I hope you benefit from these examples and you can use this in your future work. And if there are still questions, and I'm happy to answer them now. Well, if there's no further question, then I thank you for your attention, and I hope you will enjoy the rest of this practical course. And if later on you have any questions concerning the exercises or the content of my talk, just contact me by email.